Hello, everybody. Welcome back to another episode of Am I Dumb or Has the Educational System Just Failed Me? Well, have no fear. We're here to help that issue. So, let's get right into it. So, today we'll be going over types of series for linguistic learners. So, the main types of series that there are the power, geometric, alternating, and harmonic. There's also the arithmetic series, Fourier series, binomial series, Dirichlet series. But from what I've noticed is that almost every series that you would be learning probably later in your math courses are pretty much all derived from these. They may look a little bit different because they may have trigonometric terms, but generally speaking, from what I've found is that they all can be derived from one of these. So the common things across all of these series is that they all have at least one constant term. So we'll go over generally how they look and what's their format, but to refer back when you're studying or something, it's important to note that they all have at least one constant throughout the series. They all add products of mathematical phrases together. So essentially there's the algorithm, you plug numbers in, and then you add them together. And what's important to note about that is that these products have specific ranges from when to when you add. So essentially you have a phrase and you have a counter ranging from, let's say, 0 to infinity, or -3 to 4, anything really. And you plug in the counter throughout the phrases and you add them together. All of these will either diverge or converge towards a number, meaning that once you add if you keep on adding throughout the range, these phrases together, they start to either level off and approach -7, or they start to approach 5 or something like that. That means that they converge if they sort of level off towards a finite number. If they diverge, that means that the series is either going to be increasing to infinity, or it will go to -infinity, depending on if it's a positive or negative series. We'll go into conditional convergence and absolute convergence and all of that in another lesson, because that would be too much for today. Today we're just kind of going over how to identify what type of series there are. Alright, so and then so moving on. How can series be useful? So a lot of kids, they don't really understand series, mainly because they don't really see what's the point of learning it, or they don't really see why this would be useful. And honestly, I had the same problem, which is why I'll try and spare you the time of trying to look up am I ever going to use this? Do I really need to learn this? The thing with series is that there's lots of uses, but there's almost no uses at the same time. So unless it's very specific in what you're doing, mainly they'll use them in computer programming if they're processing signals or sound or video. They'll use them in electric circuits if you're building let's say a synthesizer or something similar. Where's my cursor? It's also useful. A lot of people don't mention this in, when they're teaching math in schools, is that it's useful regarding the Fibonacci sequence. The Fibonacci sequence is kind of like a representation of patterns in nature. It could be called the golden ratio, whatever, but essentially like a lot of different natural objects follow these kinds of like the Fibonacci sequence, like flowers, shells, fetuses, fingerprints, hurricanes, and it can be used to draw in applications like Photoshop or something, or if you have one of those Mandelbrot set fractal mathematics kind of applications, you can draw with that, or it can be used to weather forecast, conduct forensic imaging, or map galaxies, maybe even in the universe. These are things you can like find out, and if you're really interested, go about connecting how series kind of relate to those things if they happen to be one of your interests. All right, so now we're going to go over the formats, and then we'll go over what each variable means, and then we'll practice identifying them together. So essentially the first one, the power series, we have the sum from n equals 0. We kind of like read it this way up. The sum from n equals 0 to a number n. And we have a coefficient here that counts. So this can be, a math phrase. It can be just a constant number. It can be another n formula, like let's say n times 2 to the n over, or 1 over n times 2 to the n, or something like that. But this is generally like gonna be Cn. And then x is the it can be given, but it's more of like a useful thing to have when you're checking for convergence, because it depends on the x naught value over here, which the x naught sign is sort of like the first term, or it's what the series is centered around, the convergence is centered around. And notice the n up here. So this looks eerily similar to a polynomial. That's because power series are generally, they are representations of either polynomials or different phrases that can be converted into polynomials, and then that way you can estimate the expression better. Obviously, this here is the sign that you're going to be adding from a range down here to a range up here. Usually the range is like from 0 to infinity, but sometimes it can be from negative infinity to 0, or it can be 4 to 7, or it doesn't really matter. These two things, they just kind of help in determining the convergence. We won't really go over how to do that today, because that's also another thing. But yeah, so the next one is the geometric series. Again, we sum from n equals 0 to another bigger n. And the formula, like generic formula for this, is the starting constant times a ratio to the power of n being like we're counting up and n is always changing. So essentially, a is the first term, the very first term in the series, and then r can be found by just taking each phrase and dividing so like you divide the second phrase by the phrase that came before it, and then you can find the ratio with that. And that's the geometric series. Next one is the alternating series. Essentially, again, you sum from n equals 0 to another n, or maybe n equals -1 or n equals 1, depends when you start your counter. Sometimes it doesn't matter, as long as you just have the range and it makes sense mathematically. So we have this term over here, the -1. As you notice, we have the n up here. And as n goes from 0, 1, 2, 3, we notice that -1 to the 0 is just 1, -1 to the 1 is just -1, -1 squared is 1, and then -1 to the power of 3 is -1. And you can see here that the signs are alternating, going from 1 to -1 to 1 to -1. That's why we call it an alternating series, because each term or each sort of phrase is a different sign. And I mean, we have the coefficients here, like we said in the power series. This is sort of similar. We can have basically 1 over n times 2n, or maybe we can even have an x in there sometimes, depending on certain variables. And yeah, so that's the gist of the alternating series. And then the harmonic series, this is kind of just an example by itself in a way. This is sort of to show that you don't have to always start from n equals 0. You can sometimes you have to start at n equals 1, or maybe -1 or something like that, and then just sort of skip over 0, or, well, I mean, you have to start with 1, because you can't, okay, anyway, so essentially, the reason why you start with 1 here is because 1 over 0 does not, like, exist. You can't divide by 0. And what's important to note about the harmonic series is that you have the first term that's 1 plus 1/2 if we start counting, plus 1/3, plus 1/4, plus 1/5, so on and so forth. And the thing to know about the harmonic series is that this is 100% always going to be divergent. If you see this harmonic series, this is always going to be divergent, unless you have, maybe an alternating series in front of it, or maybe you have 1 over n cubed, or you have maybe 2n squared plus 3, and then you have maybe like n. These are not harmonic series. This one is it's a harmonic alternating series, but again, that one has to deal with like conditional convergence and absolute convergence, and we're not really going to be covering that today. So anyway, that was the gist on each format for each series. And we're going to be using these to identify series, because that's a big part in multivariable calculus, is when you're, taking a test, which I'm sure no one really likes doing, but like when you take a test, I mean, you're going to take them. The main thing to know about these things is that you just have to like sort of get good at identifying each type of series, and kind of just finding the commonalities between the 4 series that you see here. And then if you identify them good, then that's when you know how to go about solving them, or how to go about, finding if they're convergent, divergent, conditionally convergent, all that type of stuff. So, and we're not going to be going over like how to, solve them or simplify them and stuff like that, because that would be a very long video. So, just to kind of refresh, a convergent series approaches or sums to a finite number, while a divergent series sums to an infinite number. So that's the thing to note. Alright, so our first one that we're going to be identifying is the sum from n equals 0 to infinity equals 3n. Now we see that, the pattern is 3 to the 0 plus 3 to the 1, plus 3 squared, and so on. We can comfortably say that this is divergent because as you see the trend going, this goes to infinity as you keep on summing it. So, to identify this series, we're going to have to whip out each formula into our heads, look at them, and we see that this one fits most the geometric series. Mostly because here we have the first sort of term, which also happens to be the ratio. So in this case, we just essentially can rewrite this as r to the n, or a to the n. Either way, this is just going to be a geometric series. The next one might confuse, but that's okay because that's how we learn. Get confused and then we learn. So it's the sum from n equals 1 to infinity of brackets 2x plus 1 brackets n to the n. So we might be tempted to say that this is a power series. Is it? Oh, wait, no. Oh boy, I forgot. I have my notes on the board up there. What was I thinking last night? I was thinking, oh, this would be a good one because we're going to learn something from this, and then I forgot exactly what was needed to be learned. Great. Okay, we'll get back to that one, honestly. Sorry about that. Okay. We'll go over to this one over here. So this one, I mean, we've seen this one before. The sum from n equals 1 to infinity, 1 over n is equal to 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, and so on. And remember that this is divergent because it goes to infinity. We'll maybe explain in another video why this goes to infinity. But this is the harmonic series. Because it fits literally exactly the format that we were talking about. Okay. Now, next we have the sum from n equals 0 to infinity of x to the n over n factorial. So we see that this starts at 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4 over 4 factorial and so on. So what do we make of this? I mean, we could see that this fits the general format of the power series where we have Cn x minus x naught to the n, where Cn is equal to 1 over n factorial, and then x naught is equal to 0. So essentially we then can, sort of plug this into the series and say, okay, well, this is just essentially 1 over n times x minus 0 to the power of n, and that's going to be why this is a power series. And the next one we'll be going over, this is pretty similar, except now we start from n equals 1. Sorry, that's a very bad one. But it's starting from n equals 1 simply because if we started from n equals 2, this would be 1 over 0. This whole kind of expression here would be 1 over 0, and we can't have that. That's why we start from n equals 1. So if we go about identifying it, let's say we start with the power series, then we have Cn is equal to 1 over n 2 to the n. And then we have x naught is equal to negative 5, x equals x, and n equals n. Therefore, if we put this into our sort of power series formula thing, then we have n equals 1, x minus 5 to the n over n times 2 to the n. And you can see that it becomes simpler when you actually write out each of the terms, because you can see easily that, oh, this is n times 2 to the n when n is 1, or this is n times 2 to the n when n is 2, and this is when it's 3. And then you can notice that over here we have the exponentials. These also count upwards. And then you can see here that this is sort of just the constant term throughout the entire series. And as you notice, we all have positive signs here, so they're not alternating, therefore it's not an alternating series. It's all being added in a range, therefore it's a series. Sorry. Okay. Now let's look at this series over here. This is similar to the one that we just did because it fits the general kind of n equals 0 to infinity, Cn, x minus x naught, n. Because here Cn is just equal to 2n plus 1, and then x naught is equal to 0. Therefore, we can say that the series is essentially just n equals 0 to infinity of 2n plus 1 x to the n. Sorry, that's really bad handwriting. But in any case, we can see that this is sort of like a polynomial being added together. One way to identify a power series is because we have x's and it sort of looks like a polynomial. The whole thing just resembles a polynomial with like x or x minus x naught to the power of something, and then it's multiplied by sort of a constant in a way that's like counting upwards throughout the series. Or it could be counting downwards. Alright, so right off the bat we can see that this starts from n equals 1, and we have an n up here. So we know that this is going to be alternating signs, which we can see here. It's negative, positive, negative, positive, negative, positive, and so on. And once we actually just plug in each number, we see that it's essentially just this one times like counting upwards. There's no x, so this is an alternating series. And also the reason it's not a harmonic series is that 1 over n does not equal 1 over n squared. As you can see that this is n squared. That's literally what it is. Okay, so going back to this one. Going back to this one. I think I messed up the writing on that. I think that's what happened here. Yeah, I think the x was supposed to be n. Maybe I'm wrong? Actually, no. Reason why is because this is actually just a geometric series. The reason being is because if we just plug in x equals 1, we're going to get 2 plus 1 to the power of 1, that's 3, plus 3 squared, plus 3 cubed, plus 3 to the 4, and so on and so forth. And this is very eerily similar to our very first example of our geometric series over here. Sorry that took me a sec to figure out. I don't know. I slept 4 hours today and then 15 the previous day, so things are going great. Just kidding, they really are though. Appreciate your guys' support. I appreciate you watching my videos. That's it for today. That's essentially all there is about, identifying different types of series, what you can use it for, what are very common things across all of them, and what are the differences between them. Pretty straightforward kind of, linguistic approach to things. So yeah, I guess, that was it for today. Thanks for watching. See you next time. I believe on Twitch on Tuesday. I'll be changing my streaming time so that it's, there's not so much internet traffic going on. Probably to like around midday. Just putting it out there. So our stream times might change, and I'll have to update that on the website. So go to williamstechnique.com to sign up for a tutoring session if